Very good morning, one and all, my dear young and energetic researchers and professors from the various institutes. Today I am going to present on the topic of machining of titanium alloys in CNC Wire EDM using online liquid nitrogen cooling. Before going to this topic, we have to little bit touch upon these various topics. It's an overview of our my presentation. First, introduction to conventional and non-conventional machining, because we are going before going to this, we have to little bit touch because most of them know about this. Some of them, few of them, they don't know about the non-conventional machining and all. And the second topic is about the EDM, because before going to the wire EDM, we should touch upon the EDM. And then next one is the components of wire EDM and process parameters, because the major role, the process parameters is in the research, the major parameter, process parameters of wire EDM is involved. And then recent advances and technical specification and applications and introduction to titanium alloys and introduction to cryogenic treatment, why we have to go for the cryogenic treatment, and then recent advancement in research in cryogenic machining. So these are the content we covered. As soon as possible, I have to cover within the 1 hour, because it is a very little amount of time to me, because the area is more than so much more slides are there. In this very narrow time period, I have to complete within my effort. Initially, there is an introduction. What is a machining process? Before going to the conventional or non-conventional, so we have to touch upon this machining process. We people know that there is a conventional and non-conventional machining processes. So conventional machining in olden days, Stone Age all onwards, we have to start it, and then still now we are using the conventional machining also. But some of the condition we can't do the conventional machining process for some of the complex shapes and hard materials. Then we have to enter to the what is called non-conventional machining process. See here, over the previous decades, that is engineering materials have been greatly developed, because day by day life we are creating much more research is going on this particular engineering materials, because of the need of the industry. So day by day they are producing various materials. At the time we can't cut the material for the required shape or the customer satisfaction. We have to go for the unconventional machining processes. So unconventional machining process, it is also classified into various categories. Depending upon the material, we have to classify it in that particular thing. So that we have to greatly develop the non-traditional machining processes. That is cases the machining of odd materials and certain shapes we can't do, cut the or machine the help of the conventional machining, so that we have to enter into the non-conventional machining. So see here in this slide, I mentioned this hardened steels, austenitic steel, superalloy steels, superalloys and carbides, ceramics and fiber reinforced composite materials. So these are the materials having different properties. So each material having different properties, so that we need to cut the material for the required shape or customer satisfaction, so that we need a separate machining processes. So the problems in conventional machining process. What are the problems? How we have to rectify that problems? So in this problem in conventional machining, that the workpiece material is too hard and strong or tough. Okay. And then workpiece is too flexible to resist cutting forces or too difficult. So during these are the types of problems, we cannot do that particular conventional machining, so that we have to enter into the non-conventional machining. What is non-traditional machining? That is unconventional or non-traditional machining process. Okay, it's adopting a unified program to utilizing the result of basic applied research. It becomes the process of many engineering materials, already I told, which formerly considered to be unmachinable using tradition methods. See here, the small example I am telling now. So olden days, we people are using, I am telling Tamil, ammikkal, oral, they are used. But nowadays, our housewife, they are using mixie, grinder and all. That is a entire marvelous change. Okay, initially that is a big size of grinder they are using, and after that they are changing small grinder. Now it is a tilted wet grinder, and then now it is a portable wet grinder. It is a more or less change. It is also one type of unconventional and non-traditional machining process. This is an example. Okay, don't think this is a non-conventional or a non-traditional. This is an example. And then the various characteristics having this non-traditional machining, that is capable to machine, that is metallic and non-metallic materials irrespective of their hardness or strength. And with the help of this non-traditional, that is a complex and intricate shapes in hard and extra hard materials can be rapidly with high accuracy and surface quality and free bursts. Because during the machining operation, various research they conducted on the conventional machining and non-conventional also, the chip will be affect the surface of the workpiece, so that the free burst for this non-traditional machining process, we have to make it a free burst machining operation. And then the selection aspects of non-traditional machining process. So before going to the before going to select the non-traditional machining, okay, because there are three kind of process they converted. Before going to that, we have to select the material, and we have to select the process parameters, and we have to select the economic and environmental concerns. Today, the world is focusing on the environmental, that is the green manufacturing and the green studies and green environmental, everything. So we have to select these type of environmental considerations. And then the classification of traditional machining process, non-traditional machining, that is a mechanical process. Another one is a chemical and electrochemical process. Here they are the mechanical process, that is abrasion or shearing, and then chemical and electrochemical process, that is an ablative reaction where the acids and alkyls are used as agents. And the next one is the thermoelectric process. Next one is the thermoelectric process, where the metal is removal rate depends upon the thermal energy, that is melting and evaporation. See here in this non-traditional machining, I classified into three categories. One is mechanical, another one is thermal, another one is chemical and electrochemical. So they divided into, again the mechanical is divided into four categories. One is ultrasonic machining, another one is water jet machining, another one is abrasive water jet machining, and ice jet machining. So these four machining operations coming under the category of mechanical engineering. And then thermal, with the help of thermal, that is electric discharge machining and electron beam machining and laser beam machining and ion beam machining, and last one is the plasma machining. So they are classified into five categories. And chemical and electrochemical, that is chemical machining, photochemical machining, and electrochemical machining process. See, in this slide I clearly explained the fundamental energy, that is a mechanical energy, that is how they have to remove the material, that is mechanism, behind the mechanism, that is called as erosion. The material is eroded. Okay. And then chemical, that is ablative reaction, that is called as a etching process. What is the ablative means? It is defined as the removal of material from the surface of an object by vaporization and chipping or other erosive process at high temperature. That is called as an ablative reaction. And then the electrochemical, anodic dissolution, and thermoelectric, that is a fusion and vaporization. These are the mechanism behind these, all the fundamental. There is a fundamental energy, mechanical energy, chemical energy, electrochemical energy, and thermoelectric energy. And the removal mechanism is erosion, ablative reacting, and anodic dissolution, and fusion and vaporization. And before going to the wire EDM, we have to little bit touch on the what is EDM. The understand of wire cut EDM, we first need to know about electric discharge machining. What is that? The electric discharge machining is also known as a spark machining. So the spark will be appeared, and then the material will be eroded. That's the spark eroding and die sinking, wire burning, or wire tension. It is a metal fabrication process. And this material is removed from the workpiece by a series of rapidly recurring current discharging between the two electrodes and separated by a dielectric liquid. So this is this diagram shows the EDM process. We don't touch upon this. So simply for the example, I shown this particular figure. Then what is wire cut EDM? Before going to the cryogenic and the machining process, we have to go for the basic of wire cut EDM. So this is a machining process for conductive materials only. We cannot go for non-conductive. Already I told various non-traditional machining processes classified into energy, fundamental energy, that is a mechanism also. In this case, this wire EDM is used for only conductive materials, only for conductive. Please note it down. This is only for conductive materials. You cannot machining for the non-conductive materials. So it's an electrothermal production process within a thin single strand metal wire along with the deionized water used conducting electricity. So here purely deionized water only we have to use. The less cost of this particular thing. The per liter of the deionized water is 1 rupee or 0.8 paise. Okay. So 2000 liters means that is around 2000 rupees only. Okay, so we have to utilize that particular deionized water for this. It will be reused one because it will goes to tank once again, then it will go to filters and it will be what is called refreshed, and again the water goes to the purified waters go to tank. So this is a rotational process. The wire cut EDM typically used cut plates as thickness around 300 mm thickness. We have to cut it because about the thickness, it will be the time will be taken more. This is the schematic diagram of the wire EDM process. So this is a spool. It is called as a spool. This is a wire pulley. Then it's a wire guide. So it is like a stitching process. Okay, bobbin. Again, it will be goes to that particular base bobbin. Then it is a new wire. It will comes to here, and then it will machine the work pieces, and it will goes to particular after the machined wire is a used wire is rolled another one bobbin. Okay, it's a filter and pump. It will go to the deionized water flushing rate. You have to use the flushing high, medium, and fast. High, medium, and low. So what type of material we are using there, so that we have to select for the high, medium, or low. This is a workpiece. The gray color is shown is a workpiece. This is the process how the wire will move and then cut the complex shapes. Here the diameter of the wire is very thin. That is the 0.3 mm. 0.3 mm. We have to use it the 0.3 mm wires. Various machines we have. On the particular machines, we have to select the wire thickness of that particular thing. In India, we have to use recently for the past 10 years, we have to use this wire in the past 10 to 15 years, we go back. But in this era starts in the 1960s, making tools for dies and hardened steel. The first commercially available NC machine built, that is a wire EDM, is started in the 1967, and it will be connected with the plotter and optical, that is 1974 and 1976. Typically, it will be grown. This is the difference between a conventional and a wire EDM, conventional wire EDM and wire EDM. This is a material removal rate. So the theories, no need, I will share it this. This is the major components of wire EDM. Without these components, we cannot operate this machine. The computer numerically controlled, it is called as a brain of the system. It is called as a brain of the system. And then power supply, it is a muscle of the system. It is like a human body. There's a computer numerical, everything is stored in the brain, and it will go through the muscle. That is the power supply. With the power supply, and then mechanical energy, mechanical section is called as a body. So brain, muscle, body, it will work on this. And then dielectric system. Okay. So here in this diagram, in this figure, I shown this computer, that is a CNC one. Okay, everything is we have to store here. That's around 20 programs we have to store. Here. Around 20 programs we have to store here. And then when we have to need, then we have to retrieve the program, and then we get modified, and then we get store it. Okay, no need to go for the program writing and all. We have to set it here itself. Otherwise, we have to 2D program, that is AutoCAD, and then we have to insert with the help of a toggle. It will be converted into that particular pictorial diagram. Then we have to do for the any complex shapes we can machine with the help of this machine. So without AC, see in this diagram, see here without AC current. Okay, without AC current, with the use of DC current, what has happened? While the machining of titanium alloys, using the DC circuits, we get the blue discoloration. So we see here in this blue discoloration is there. This can be avoided if you use AC circuit instead of DC circuit. So avoid the DC circuits when we can get the great machining. The functions of a spark generator. See in this figure, I shown in that particular machining operation for the thickness of the 300 mm workpiece. Okay, supplies adequate voltage to initiate the spark, so that separate transform given to this particular machine to regulate the intensity of current. We have to regulate and regulate the spark duration and to control the recurring rhythm of spark. So here in the spark energy settings, they have to shown in 18 to 16. So higher range to lower range, that is for 3.3 mm wire. Sorry, and 15 to 10, that is for rough cut, and 9 to 5 there is a second cut to improve the tolerance, and 4 to 1 is the third cut of better finish. So better finish we have to go for very less. So the mechanical section, that is a pulse generator, work table, taper unit, and wire drive mechanism and wire electrode we are having. So this is a explanation of the pulse generator and work table and the taper units, various things. So see here in this diagram, wire drive mechanism, they use to this wire EDM machine, they cut the wonderful and very soft, good surface finish of the what is called a gear. This is the basics of wire order, how the deionized water flush and how the material will erode. These are the things. This is the wire path. This is called as a wire path. So here in this wire will move between the workpieces. The blue color is the workpiece. Okay. So the wire dragger, during this particular machining operation, we should have very good tension between the so very good between the tension. Very good. We need the very good tension for the wire. Without the tension, it will be get losing. That we cannot machine that particular object. Otherwise, it will be make a very worst of the objects. So the effect of wire drag. Okay, desired part shape is this one. So ideal path, no wire drag using slow cutting, speed or automatic corner cutter. So it is a perfect one. If it is not a perfect, then the wire will go. If it is loosened, then the wire will goes to like this, and the machining will happen like this. So it is called as a failures. Okay. So how to avoid the wire drag? Skim pass with the high tension. Okay, skim pass. That skim pass means the wire passed back over the roughed surface, again with the lower power setting and the lower pressure flush, and slowing down the feed rate, and the program dual can be introduced, and smaller gap voltage providing longer distance between the nozzles. In this particular wire EDM machine, we have 4 types of wires, that is copper wire, brass wire, coated wire, and fine wires like molybdenum. So in this majorly we use copper, brass, maximum major use brass and zinc coated brass wires. Molybdenum, that is a separate machine is there. That machine alone only we have to use this particular molybdenum. The molybdenum wire is not possible to use in this particular all the major wire EDMs. Okay, this molybdenum wire is separately used for the separate machine. This is the copper wire electrode. The spool, entire spool is having a 5 kg. Okay, 5 kg of this particular brass wire. There is a 5 kg of brass wire. In the brass wire is having soft and hard brass wire, and then the brass wire is zinc coated also, soft and hard. Both 4 types of wires used for the machining operation, and then coated wires with the electrodes. This is called as a molybdenum fine wires. This is a dielectric system. The functions of dielectric. So when the machining will happen, when machining is going on, at the time the burrs will become that will be removed with the help of the flush of water, dielectric fluid. The properties of dielectric fluid: there is a low velocity, low viscosity, and good wetting characteristics, and chemically inert and non-toxic, should not form easily. This is a wire working of wire EDM, traveling of the wire. It's a various stages working of wire EDM. The major, so now we are entering into the major of the wire EDM, that is a pulse on. This is called as a parameters. We have to fix the parameter, then we have to get it the optimum values, that is for the particular machining machines, the machining the components. The pulse on time, there is a major role, pulse off, wire tension, wire feed, and peak current. So these are the major process parameters for affecting the machining. So we have to fix it in perfect manner, then we have to get the optimized values. Pulse on and pulse off, and wire tension, wire feed, and peak current. The factor influences of the wire EDM. So the machining, what are the final output? That is a material removal rate and surface integrity and overcut usability of the workpiece. Okay. The various effect of wire tension and then effect of thickness of wire. This submersible cutting process recent advancements. Okay, in submersible cutting, a tank surrounds work area and the tank is filled with the deionized water before cutting and takes place. In a dry machine, water needs to flow from the nozzle to surround the wire with the deionized water. Submersible cutting is a great aid in starting a cut and when a skim cutting process, because the wire is always submerged in water as shown in figure. So application of submersible, that is a cutting layer taper angles. So in a dry cutting, it is very difficult. So that the submersible, we will go to submersible, that is a cutting taper angles and tall workpieces and laminations and tubes, irregular shaped parts and workpieces with undercuts and cutting very close to the edge of workpieces. This is the machine setup we have. Our MIT in my lab, under my under me, this lab is there. I am the in charge of this lab. Particularly, we have used we using this particular machine is MaxiCut. It's called a MaxiCut machine. So here we have to fix it on feed and the wire tension, and then the flush rate of the water. This is the entire thing. This is a numerical part. This is CRT display. We have to take down the stored programs, and so in this particular part, that is called as a wire spool. In this place, the unused wire spool before use wire spool is fixing here in this particular leg. It will come and then here machining, and after that it will goes to used wires are stored here for the another spool. This is a consumed wire spool. Okay, this is called as a wire spool. See here in this arrow mark, and this is called as a work table. It will be goes to X, Y, and Z axis. These are the technical specification of MaxiCut wire EDM. And the need for wire cut EDM. What is the need of wire cut EDM? We have go for this wire cut EDM that we have to get good shape accuracy and no burst generated, since the because no cutting force are present. Wire EDM is ideal for delicate parts and no tooling is required. That is, wire is a tool. So delivery times are short. Pieces over 16-inch thickness can even be machined. Dimensional accuracy is not affected by heat dissertations. Can produce complex shapes and parts requiring thin tolerance, parts where bursts cannot be tolerated, thin or delicate parts that are susceptible to tool pressure, and progressive blanking and trim dies, extrusion dies, precious metals, narrow slots and keyways, and angle and tooling for forging and or injection molding operation, and medical and dental instrumentations. In this case, I also did the medical instrumentation for that particular machining with the help of this machine. And now it is a major why we have to go for titanium. That is an introduction to titanium. Titanium alloys are also contain a mixture of titanium and other chemical elements, such as the alloys have a very high tensile strength and toughness. They are light in weight, have extraordinary corrosion resistance, the ability to withstand the extreme temperature. So that today's researchers, most of the researchers enter into the titanium alloys. And titanium alloy are hard and prone to oxidation at elevated temperature. Hence, CNC wire EDM is employed to machine them. The titanium also have a wide range of application in aerospace, marine, and biomedical fields for their strength to weight ratio and corrosion resistance. This is the titanium grade 2. It is also called as a pure titanium, but it is classified in the titanium grade 2. It is also unalloyed. It is also known as unalloyed. The titanium which has excellent corrosion resistance and good formability and high strength and other commercial pure titanium. It is used for manufacturing a turbine blades, armor plating for military vehicles, and the composite for dental implants. Okay, this is a composition of the titanium, that is carbon content, iron content, oxygen content, nitrogen, hydrogen, and the remaining is a balance of the titanium. And next one, in this case, we identified that is a grade 2 and grade 5 and machined with the particular thing. The titanium 5 also having it is called as alpha and beta phase. It is located in the phase diagram, that is alpha and beta phase diagram. Alloys which has both alpha stabilized and beta stabilizers. Okay, the grade 5 titanium alloy finds the application of biomedical implements and the critical corrosive resistance components in aerospace. In this table shown in that particular composition of the titanium, aluminum, vanadium, iron, and oxygen and titanium balance. So in this particular slide, okay, in the where how much titanium are used in the aerospace. See here, the alpha and beta titanium alloy known as ASTM grade 5 titanium alloy consisting of the carbon, aluminum, which are the percentage amount. Okay, this having a high strength, good corrosion resistance, can be hard worked, can be welded, everything we can do in this particular thing. So in this case, where they are using the composites, they are using 50% and titanium is 15% of these aerospace industries. Understand? And 10% steel and 5 other materials and 20% aluminum, and because of the cost they are using very less amount, and the production of the titanium also very less, so that they are using a very so in this yellow mark, the yellow or orange mark is denoted as a titanium usage of this particular thing. The problem with machining of titanium, we prefer that particular titanium, but we can go for machining. It is very tedious because it is very hard. Then comparing the machinability of steel and titanium under lubricants, it was found that heat generated at the tool chip interface is nearly 80% for titanium, which reduces its machinability. Because the titanium alloys are hard and prone, already I told, oxidation at elevated temperatures. Because the titanium have low Young's modulus, which causes a spring back and chatter during the machining. This can create a poor surface quality in the finished products. Because of titanium, high work hardening tendency and thickness of the alloy, long continuous chips are formed during turning and drilling, so that we go for and conventional machining. See, these are the non-cryogenic machining. Already I told that. See here, without non-cryogenic machining, the ordinary machining process, what happened? The heat affected zones are formed here. In this particular picture, is experimental picture workpieces, the machined workpieces for non-cryogenic. Heat affected zones are prominent in a non-cryogenic of titanium workpieces and shown below above. Okay, these are the another disadvantage of non-cryogenic, which is overcoming the machining with LN2 cooling. And the solution to overcome the difficulties in machining of titanium, we have go for wire EDM process, okay, with the help of LN cooled brass wires. Into the cryogenic treatment, the cryogenic treatment typically involves a deep freezing process, usually one that takes object or down below the -196 degree and changes the molecular alignment of the material structures. Because the helium, hydrogen, neon, nitrogen, oxygen, argon, krypton, and xenon, methane, ethane, propane, and normal air can work as a cryogenic cases. But in this case, we have to use nitrogen. Liquid nitrogen is most commonly used element in cryogenic. It produced industrially by fractional distillation of liquid air and referred as LN2. Recent advancements in the research of cryogenic machining of superalloys. So, Northern American research, the cryogenic, it is the major role they are using this cryogenic. It was conducted the cryogenic cooling plays a significant role in reducing notch wear at higher cutting speeds. These are the various papers in North American they did on this cryogenic. After the extensive of literature, we collected this particular thing. It was also found that the cryogenic cooling decreases the amount of cutting forces required as compared with the machining under a dry and preheated condition. A technique for machining of advanced ceramics using liquid nitrogen LN2 cooled polycrystalline cubic and boron nitride tools in conal alloys. So we have to, with the help of this cryogenic, we have to machine various materials. It was found due to the cryogenic cooling, the temperature in the cutting zone is significantly reduced. Therefore, the strength of hardness of the tool at elevated temperature remains high. The surface toughness gets significantly reduced while using the cryogenic coolant. When we machined this particular thing, but we need, before going to this LN2 using, okay, we need the skilled person, otherwise it will be making a major accident, because the nitrogen gas, you people know it is very dangerous. Without, because also in this case we are using a spark, there is a spark, it will be get fire, so that we have to need a separate setup for that particular. Before going to use this liquid nitrogen, we should have precautions. We should go for precautions, preventive, everything. Otherwise, it will make major accidents. So it was observed the combination of two micro nozzles provides the best effective cooling while using the LN2 flow rate. This is a research for North American. They did most of the research. And in European research, they are also conducting various machining parameters with the help of this machinings, with the help of LN2. The experimental investigation, the tool wear pattern while machining cobalt-based superalloys, INS 25 under cryogenic cooling condition using uncoated carbide tools. These are the carbide tools, conventional machine tools. But we discussed only for the wire. Okay, that is a wire EDM. Results showed that due to cryogenic cooling, maximum flank wear was approximately 60% lower than the tool wear values obtained from the dry cutting. So, everywhere you use the cryogenic, then it will give a good result for that. Another researcher states that the cryogenic machining offers improved machining performance by providing reduced tool wears. So it is absolutely correct. So we also did the same thing, and we identified that is the performance is very good. And then Asian research, so in the Inconal 718 they are using, and then the implementation of cryogenic coolant can significantly decrease the amount of heat transferred to the tool and substantially improve the surface roughness when compared to dry machining. And reduction in cutting temperature is significant at lower cutting speeds. See here, in the another one research meant that the carbide inserts produced better surface integrity of the finished products with the cryogenic. Then Australian research, the cryogenic machining produces thinner chips as compared to the dry machining. And then the result is the effect of cryogenic compressed air on the cutting forces and chip formation reduces with increases in cutting speed and fit. See, in this European, Asian, and North American research, they are did only on particular conventional machining, that is a chip and the tool and all. So here, in this case, in this case we did that is a wire EDM. We using the cryogenic treatment. Reason for choosing the cryogenic: increase the wear resistance of material, changes entire structure, not just surface. Refinishing or regrinding does not have any impact. Closes and refine grind structures to create a denser molecule structure. Transforms soft retained and austenite to martensite, forms microfine complex, and increase the performance and durability, decrease the residual stresses in tool steels, increase the tensile strength, toughness, and releases the internal stresses. This is a normal experimental setup without liquid nitrogen cooling. I will show now. So this is a CNC unit. Already I shown that. This is a wire driven system, drive selection, and then work material mounting table, and work table movement and control unit, and dielectric fluid supply tank. So this is the process of machining, how it will be machined. The spool, wire spool, then it will be coming to this, moving the wire with these wire gates, and after that machined wires are stored in the wire spool. Okay, this is a wire diameter and gap width. This is called as a kerf width. This is a workpiece. It will the motion of the workpiece. The dielectric fluid supply of the with the help of the nozzle. See, in the setup we have in our lab, this is a original setup. Okay, we have we did the liquid nitrogen machining in our lab. We get the result. So in this forthcoming slides we discuss about this. So in this tank, that is a 50-liter capacity of this cryogenic can. It is very safe can. It is called as a flask, cryogenic flask. The cost of the flask is 50,000 rupees. The cost of the, once we have to get this 50,000, we can store it 50,000 liters of 50 liters can. The cost of the can is 50,000. We have to store it 50 liters capacity of the liquid nitrogen. Okay, this is the setup we have used. With the compressor unit, we have to pressure it. Compressed air will be goes to this particular tank, and then it will be moved to this particular with the help of the pneumatic hose. It will be go to store this machining operation. So the next slide I will show this. So with the help of this compressor, the compressed air is going to this particular place, this tank, the air molecule and nitrogen, liquid nitrogen molecules. Okay, it will be mingled with here the tank, and then it will goes to cooled air will goes to that place, and then machining will be carried out. In this case, see the measurement. Okay, initially I measured that 28 degree, then it will goes to minus 196. So with the help of, we have to measure, we use the thermocouple, separate thermocouple unit on this particular thing. This is the technical specification of the liquid nitrogen cooling setup. That is a compressor and a cryogenic 51.5 liters. The tank empty flask is 15 kg. Okay, holding time is 120 days. We have to store on the particular cryogenic liquid with the proper shielding unit. Okay, that material. Another one is the material we used, that is stainless steel for a small case. The pneumatic liner is made of polyurethane and Festo pneumatic regulators. Then thermocouple unit. This is the setup when we did that particular material machining. This is a separate tank that is made of stainless steel. Inside stainless steel we used for the thermocol as the storage tank. We have insulated with the thermocol, and then we have separate what is called closer is there. Okay, see in this particular light one, that is the wire. Okay, it will be entered here. When we conduct the trial and error method, directly the material, the wire will touch on the cryogenic. What happened? The tire, what is called that wire will get failure. Wire get failure. So that we identified that failure during the trial and error. After that, we have to go for this setup, and then we used a copper tube, that is a 0.5 mm hole in that particular copper 0.6 mm, because the 0.3 mm wire will enter into the particular thing. Then we have to store it here. That is a 150 ml of liquid nitrogen. That is it is called as a feeding unit. We have to fix it in the particular bar, and then we have to pour with the help of that particular compressor. Then we have to close this. During the each and every pieces, we have to fill this 150 ml of liquid nitrogen with the help of skilled people. This is the setup. So inside, that is insulation, that is thermocol, this is stainless steel, and the copper tube. It's a pictorial diagram we used on the particular machining operations. Then experimental work we used, that is a two grade. One is already I told, the grade 2 and the grade 5. So in this we have machined with the grade 2 and grade 2, that is brass wire and cryogenic treated brass wire. Similarly, normal zinc coated brass wire and cryogenically zinc coated brass wire. The four types of that is 4 different types. That is each experiments, that is 20 experiments we conducted for the RSM based on CCD composite central composite design. So we get the values here. The red mark, that is 14. The 14th experiment, that is the pulse on time is 8 and the pulse off time is 3. And the white tension is 1300. We get the better MRR and better RA, that is surface roughness for the brass wire. In this case, the brass wire with the liquid nitrogen in the 6th experiment, that is the pulse on time is 9 and pulse off is 2 and 1300. We get the 3.2, that is the best MRR and best RA. Similarly, for zinc coated brass wire and liquid nitrogen brass wire, we identified and we did that. Similarly, for grade 5 also, the 4 different types of experiments. That is each experiment, that is totally 80 experiments. For zinc coated brass and zinc coated brass, brass, liquid nitrogen cooled brass, zinc coated and liquid nitrogen zinc coated, that is a grade 2, that is totally 80 experiment. And similarly, in this grade 5 also did 80 experiments. And after that, the comparison of results. Okay, that is a comparison of result grade 2 machined with the wire EDM with brass and online liquid cooled brass wire. That is non-cryogenically treated. The maximum MRR is 2.64 and RA is 3.65. Cryogenic treated, that is 3.2 and 3.25 of MR. That is an increase of the response is 22%. It will increase. It was increased, and the MRR is also 11%. And then similarly, zinc coated brass wire and zinc coated brass wire with the liquid nitrogen cooling, that is a 17 and 11% of response. So this is a wonderful increasing the machinability and the surface toughness. Similarly, carried out the experiments, we had 15% of response for MRR and RA is for 8% in the normal machining. Okay, non-cryogenic treated wire, and this is also non-cryogenic and cryogenically treated wire. It will increase the 15% of MRR with the liquid nitrogen cooling. See here, this is a liquid nitrogen cooling, and 18% of RA. That is surface, a good surface finish we got. These are the various graphs. With the graphs, we identified these things for MRR and for RA for grade 2 and grade 5. As the pulse on, what are the inference we got from this thing? That is, as pulse on time increases, more discharge energy is generated, which causes melting and evaporation of the material, leads to deep penetration on surface of materials. See here, the thermal conductivity of cryogenic treat wires increases with the causes of heat in inter-electrode gap to dissipate at faster rate. Hence, MRR increases when the wire is cooled using cryogenic treatment. When the pulse on time increases, the amount of discharge energy increases. The zinc starts melting, which provides a large gap flushing of material. Hence, MRR increases. The application of online cooling reduces this, increase the temperature and decrease the thickness of titanium oxide layer, which further increases the machining rate. Similarly, for all the experiments, TA grade, when machining of grade A alloy, increase the thermal conductivity, leads to dissipate the heat at faster rate with the causes of material removal faster, but even hence the surface roughness decreases with online liquid cooled wires. Similarly, carried out various things. So better surface finish and MRR we got with the help of liquid nitrogen cooling. So in this case, the increase the wire tension reduces the transferal vibrations on the wire, which causes homogeneous spark erosion and leads to increases in MRR. The MRR produced by LN2 cooled zinc coated brass wire was higher than untreated zinc coated brass because of its higher thermal conductivity. So this is the surface topography of titanium grade 2. Large number of cracks were formed due to uneven thermal loading produced by brass on the specimen. Then uneven thermal loading is due to the improper spark formation and low time for flushing of the debris. See, in this surface topography, this microstructure, okay, that's a scanning electron microscope image, okay, titanium grade machined using brass wire. See, the globule and crater is formed here, okay, craters, the three, and the crack is formed here, and blowholes are formed, okay, large number of craters, okay. In this case, the next one is online liquid nitrogen cooled brass wire. So lump of debris, deep craters and cracks, very low only. As the thermal conductivity increase the heat, and inter-electrode dissipates at faster rate than between liquid nitrogen cooled wire and workpiece, causing the evaporation of material and forms a lump of debris on the surface. And the next, this some image shows the zinc coated brass wire, lump of debris and craters, cracks, blowholes and debris. Okay, and it is liquid nitrogen zinc coated brass wire, deep craters, blowholes and cracks it is formed. And then the cloning produces uniform discharge, because when you are using the liquid nitrogen, that the discharge of energy is uniformly wire and electrode, which results the reduction of electric field difference, causes better surface finish. Better. Similarly, we carried out the same images on the surface topography of titanium grade 5. As the titanium grade 5 is harder, all people know about the titanium, how it will be have more strength on hardened. The energy is developed during machining was not sufficient against the surface roughness is more than the TA grade 5. So the large craters are formed on the surface for the normal machining process with the help of with the brass wire. This is the online liquid nitrogen brass wire, so it will be reduced to the very few lump debris and globules and cracks. And zinc coated brass wire, again we have to test it with the zinc coated brass wire, machined with the zinc coated brass wire. The deep craters and cracks and debris is formed. This is the final one, that is liquid nitrogen cooled zinc coated brass wire. So in this microstructure we observe the craters and globules are formed, but the surface roughness is lesser than previous. The reason, what is the reason behind this? The reason is when the zinc coated brass wire is cooled using online liquid nitrogen, the properties of wire improved, future and better surface roughness is obtained. That is the final conclusion. The result, we have get the good result with the help of liquid nitrogen cooled for titanium grade 2, and as well as similarly we have to get the good result of machining of grade 5 also, that is using of LN2 cooled zinc coated brass wire use. This is the final conclusion. Thank you. I thought correct time I have to complete. I should complete